In this video, we are going to see regarding the design of cantilever slabs. In the previous videos, we have covered design of one-way slab and two-way slabs. So let us start with the design of cantilever slabs. So cantilever slabs are commonly used for chhajjas and balconies projecting from the wall face or from the lintel beams or from the floor slabs. So if you see now chhajja and all, we will be having certain projection, or like if you are going to have any balcony projection and all. So that time we'll come across this cantilever slabs. These slabs are generally designed as one-way slabs as a cantilever fixed or continuous at the supports. Uh, Earlier to what we have used in the design of one-way slab and two-way slab, basically the concept, the steps will remain same. So there will be slight changes. So first we'll try to assume the depth which is selected based on the span to depth ratio, which is selected as 7 as we have seen for the earlier slabs also. So same provisions for cantilever, it is being given as 7. The reinforcement is provided in the slab at the tension phase should be checked for anchorage length near the support. The reinforcement what we are going to provide, if you see, this is the projection what we have, the top reinforcement what we are going to provide, it has to be checked whether we have provided proper anchorage or not, like this. The thickness of the cantilever slab is generally, it is going to vary from maximum at the fixed end to a minimum of 100 to 150 mm at the free end. Distribution steel is provided in the transverse direction. Proper selection of the depth and detailing of reinforcement will safeguard against excessive deflection and cracking of the cantilever slab. So like proper, like as it will be cantilever, so therefore proper reinforcement which has to be provided at the top, proper anchorages has to be done, or anchorages like this it has to be done, so that we can avoid the excessive deflection or cracking. So we should take care while placing the reinforcement or while doing the detailing of the cantilever slabs. And this cantilever structural element should be checked for safety against overturning. So whenever you have to have the slab and all, when you apply the load, so probability will be having of overturning and all, for that also we have to check. So now let us try to solve the problem. So design a cantilever slab projecting 2.1 meters from the support using M20 and Fe415 steel. So we are going to have now one cantilever slab which is having projecting at up to a distance of 1.2 meters. So cantilever projection is 2.1 meters, M20 grade of concrete and Fe415 steel we have. So let us try to solve the problem. So first let us try to select the effective depth, that is L by D ratio, that is span to depth ratio. You can have it as 7 or you can have it as 10 also. So if you use it as 10, so therefore depth will be equal to span divided by 10, that is 2.1 meters divided by 10. So we are going to get answer as around 210 mm, 210 mm. So what we can do, we can provide two depths, uh, like we can provide one trapezoidal section like this. So here we can assume a depth of 120 mm at the free end and 240 mm at the support end, which is supported or near the face of this supports. So if you take average, it will be like 180 plus we can have some cover and all, so it will be like overall depth will be, average overall depth will be 215 mm. So that D will be 240 mm at the supports and which is reduced to 120 mm at the free end. So the next is load calculation. So if you calculate the self weight of the slab, so we have to take we have taken like tapered section, 240 mm we have near support and 120 mm at the free end. So we have to take average depth, that is 0.24 plus 0.12 divided by 2 multiplied by density of concrete, that is 25. So we'll get answer as 4.5 kilonewton per meter square. So let us assume a live load of 2 kilonewton per meter square and floor finish of 1.5. Then next, if we are going to add up these three loads, we are going to get the total working load that will be equal to 8 kilonewton per meter square. So therefore ultimate load will be equal to this load multiplied by 1.5. 1.5 multiplied by 8, it will be like 12 kilonewton per meter square. Then next is we will try to calculate the ultimate moment. So as it is a cantilever, as we know, so maximum moment we will be getting as WL square by 2. So therefore 0.5 multiplied by W is 12 and L is 2.1 square. So we'll get answer as 26.46 kilonewton meter. This is the ultimate moment. So based on this moment, let us try to check the depth which we have provided, whether it is satisfying the criteria or not. So mu is equal to 0.138 FCK BD square, as we have Fe415 steel. So therefore depth D required will be equal to mu divided by this value is 0.13 FCK BD. So here we are going to take B as 1000. Why? Because we are considering this as a slab section of 1 meter and we are designing. So FCK is 20.138 divided by mu. So if we calculate, D required will be 98.9 mm, which is less than 215 mm, which we have provided. So therefore our depth what we have provided, it is sufficient to resist the design ultimate moment. Then next let us try to calculate the AST minimum, that is 0.12 percentage of gross area, that is B into D. B is 1000 and D we can have it as 240 maximum depth. So therefore requirement will be 288 mm square. This is the minimum area of steel that has to be provided. Then next is let us try to calculate the reinforcement based on the moment. 26.46 is the moment which is coming. This is ultimate moment. So we can use another formula, or we can use this formula also, so as to calculate the moment. If we calculate, we'll get answer as 305.6 mm square. So for this, if you are going to use 10 mm dia bars, we have to calculate the spacing, that is pi by 4 into 10 square divided by AST required, that is 305.6 multiplied by 1000. So you'll be getting approximately spacing as 255 mm center to center. Then next is the minimum next is regarding distribution steel. So minimum area of steel is 288 mm square. So based on this, if you are going to provide 10 mm dia bars, that is pi by 4 into 10 square divided by 288 multiplied with 1000, we will be getting answer as around 270 mm center to center. Then next, as we said that it is a cantilever, so therefore what reinforcement we are going to provide, it has to be checked for anchorage length. So already this also already we have studied in the anchorage length. So once again you can refer same formula we are using, development length, that is 0.87 f of y divided by 4 into tau into bd to 5 we have. So already we have seen all these things, how to calculate the anchorage lengths. For this calculation you can refer that video in detail, already we have covered. It is 0.87, f of y is 415, 4 into tau bd, that is 1.5 multiplied by 1.6 multiplied by 5 be 10 mm. So therefore this answer will be 470 mm. So therefore this proper precaution or care has to be taken while providing the anchorage length. So therefore what happens is that the main tension reinforcement which is extended into the support should be up to a minimum length of 470 mm, including the anchorage value of hooks and 90-degree bends. So what anchorage we are going to provide, it has to be 470 mm, which is inclusive of what hooks and all if you provide and bends if you provide. Then next is we have to check for deflection. So L by D maximum is equal to L by D basics multiplied by KT, KC and KF. So if you want, this will be 1, as this is for KC and this is for flange section compression reinforcement, this is for tension reinforcement we have. So this we will try to calculate. This will be 1 and 1, this has to be calculated. So for that we have to calculate the percentage of steel, that is AST, that is 305.6 divided by B into D, that is 1000 into 215 multiplied by 100. So we'll get answer as 0.142. This is the percentage of steel what we have. So based on what you can say, if you refer the IS456 2000, many times you have calculated this KT value. So if you refer, we'll get KT, it will be equal to 2, KC and KF will be equal to 1. So therefore these values if you substitute here, so that is L by D maximum will be equal to L by D, which is given in the code book, is 7, that is 7 we can have. 2 is KT, AC and KF are 1, so that value will be getting it as 14, and L by D provided, that will be equal to L is equal to 2.1 meters divided by D provided is 215, so which is equal to 9.76, which is less than this 14. So therefore our slab is satisfying the deflection criteria which is given in the code. Now this is the ultimate detailing what has to be done. So you can see now this is the tapered section. At the support, near the supports we have provided 240 mm, at the free end it is 120 mm. So now as it is a cantilever slab, so proper care has to be taken that this has reinforcement what we have calculated, it has to be provided in top as it is a cantilever beam. So now you can see now this is the main reinforcement, which is like 10 mm diameter to 55 mm center to center. Now the circles what you are seeing, this is nothing but the distribution steel, which is 10 mm diameter 270 mm center to center. The length of the slab projection is 2.1 meter. This way we have to do the detailing of the slab.